it's 3:05, so let's get started. So just a few quick announcements. Quiz 3 is out and is due on Saturday night as was for the first two quizzes. Part 2 of the homework is due on Sunday, so just a quick survey, I guess. How many of you actually did part 1 or some of part 1? Okay, so for those of you who didn't, I highly recommend doing them because we're going to provide really good feedback if you happen to not be doing something correctly. So I highly recommend doing part 2. And solutions to quiz 2 and recitation 2 are also on the website. So any questions before we get started? Anything about the material, anything, this is the time to ask questions. Okay, so what was the main thing that we talked about in lecture last week? Yeah, these things called NFA. So what's an NFA? What's the acronym mean?
Non-deterministic.
Yeah, non-deterministic.
FA.
Yeah. Fun acoustics. All right. So, well, I do understand the deterministic finite automaton part, but what does the non actually get us now? What does it give to us? Yeah, so something with empty string, but more generally we have choices, right? I have choices, I can choose to do a particular transition. So what are the types of choices that we can have with NFAs?
If you're at a state, you could have any number of inputs. So like, before there's only like one path out of a single state in the DFA. Now you can have branching paths.
On a particular symbol, yes.
Okay, yeah.
Whereas here, I can have multiple transitions on the exact same symbol from the same state, right? So multiple transitions from same state, same symbol, right? And then just graphically, what this means is that if I have a state Q1, I can have 2 transitions on the same symbol to multiple states. Multiple different states, yes. Okay, well, is that the only choice that we have?
Yes, sir.
Yeah, we have these epsilon transitions. So what is the rule of epsilon transitions?
It's like we can't skip one.
Yeah, so if I choose to take this transition, I don't have to. If I choose to take it, then I don't read anything off the input when I actually perform the transition. So I have an epsilon transition. And so that gives us some more power. All right, so that seems quite nice to be able to define NFAs in terms of, well, it's the exact same thing as a DFA, but with these adornments. Okay, well, why even study NFAs then? Because I claim I can't build such a thing because I need to be able to choose which transition to take, and I can't do that unless I explore all possible options. So I can't build an NFA in practice. So why even consider these?
Creating a DFA from NFAs.
What was that?
Creating a DFA from NFAs.
Yeah, I can convert an NFA to a DFA, right? But that's just complicating the issue, right? I could have just dealt with DFAs. If this is true, I could have just dealt with DFAs from the start. So why even bother with NFAs?
Isn't it easier to union them and concatenation?
Ah, so what were the 2 operations that were kind of hard to do with DFAs?
Union and intersection.
Well, we know how to do them for DFAs, but
Oh, star and
concatenation, right? So this is the real reason why we study these. So we have concatenation and star. And why do we study these? Because it was so easy to do this for NFAs, and we didn't see how to do it for DFAs. But combined with the fact that we can convert to a DFA, now we can actually confirm to say that the regular languages are closed under concatenation. Whereas before we introduced NFAs, we couldn't really say that. So that's the real reason why we study this. Okay, well, since I said these were pretty easy and we have exercises to do them, I think we should understand how we did the NFA to DFA thing, because that's what's the most crucial thing here. Okay, so how did we actually do that?
You kind of had to like turn an NFA into a box.
Yeah, so we had to convert to a DFA, and we want this DFA to simulate the NFA somehow. So maybe let's try to make this more formal. So let's say we have an NFA Q sigma delta Q0F. And what we want is a DFA with the exact same language. So I have a DFA that I want to get with some other states. I'm probably going to change the states. I'm definitely not changing the input alphabet because I want the same language. Different transition function for that reason, different start state, different final states. And now I just got to define those 5 pieces. So now I just got to think, how am I going to actually implement this as a DFA? Well, let's look at this. Let's just call this top state Q2, this bottom one Q3. Well, in a DFA, do I have choices? No. So for a DFA, if I was implementing this as a DFA, I can't have this. And I have to have a transition on a particular symbol, A. Well, maybe a good idea is to look at these 2 transitions, or maybe more if there are more, and collapse them down to a single state, right? Because if I have a lot of these, then I could have chosen any number of any one of those, right? So why not just put them all together as a state? That seems like a perfectly good idea. Well, could I have a transition like this to every single state of the NFA? From one state? Am I allowed to do that? Yeah, just because I said multiple transitions, that doesn't mean I have some limit other than the number of states themselves. So I could conceivably go to every single state in the NFA. Could I go to no states? Yeah, like for instance, this state, or even this state. Q2 doesn't have a transition on anything, right? So if I try to take a transition, I end up nowhere. So I need to be able to handle all of those at the same time. Could I go to a subset of the set of states in the NFA? Instead of going to every single one or none, could I go to something in the middle? Yeah, like here. If I have other states, then I'm only going to 2 of them, which is the subset. Okay, so maybe I need to think of this as I can go to any subset of the set of states. I'm not going to bar any possibility. So what is the set of all subsets? Power set. And I think I should be doing this over the set of states in the NFA. Because I want the DFA to think of each state as being a set of states in the NFA, and then we relate these sets together. Okay? Okay, so alphabet's the same, that's no problem. Now I gotta define the start state. So I'm gonna ask this question several times. What are states in the DFA representing in the NFA? They're representing sets of states. Remember, it's the power set, is the set of all subsets, right? So I think the start state of the DFA better be a set, right? Because there's sets of states in the NFA. But then I gotta figure out what's gonna go in this set. How do I find out what should go in that set?
It's the subset of the start states of the DFA?
Well, this is the start state of the DFA, and I'm going to put states of the DFA in here, of the NFA, sorry, in here. But what states of the NFA should go there? What state definitely should go there? The start state of the NFA, right? That better go there because I want to have the same language. So I'm going to have the start state of the NFA right there. Okay. Is there a problem with this? Is there a problem with that?
Include the epsilon.
Oh yeah, let's think about it. Does a DFA have epsilon transitions?
No.
No, right? I don't have that choice. So maybe I could have the possibility of having my start state having epsilon transitions. And I definitely can't have that in an NFA. So how am I going to fix this?
You have that special epsilon function.
Oh yeah,
We talked
something
about-
with trying to find where you can go via epsilon transition.
Epsilon closure.
So something called the epsilon closure. So let's see what that means. It means, well, I could be here, right, without having read anything. Could I be in Q1 without having read anything?
Possibly.
Yeah, I have the freedom to choose to do so, right? So, in a DFA, I gotta have all those choices down to a single state, the start state of the DFA. So what was suggested is the epsilon closure. So I look at Q0, the set containing Q0, and I say, where can I go on epsilon transitions? Here, it's Q0, Q1. So just as an example, the epsilon closure of Q0 is what here, in this particular case?
The set containing Q1.
Set containing
Q1.
Q1 and Q0, right? So epsilon closure means everywhere I can get to with epsilon transitions. I don't have to take them, right? So I could just stay here in Q0 if I wanted to. So I think I should put the epsilon closure of Q0 in, right? That seems like a logical thing to do because I may have situations like this. Okay? Does that make sense? Okay. Let's define the transition function. What does the transition function of a DFA take as input?
A character from
The character and a state, right, of the DFA. What does the state of a DFA represent in this case? Set of states of the
DFA.
NFA. Good. So this S that I'm going to write here, I should give it a different name because this looks like an S to me. So XA. So X is going to represent a subset of the set of states of the NFA. But what is it in the DFA? A single state, right? Because that's what the states represent. So now I got to figure out what state of the DFA am I going to go to, or what set of states am I going to go to in the NFA? So it may seem daunting at first, but let's look at an example. So I have this NFA right here. And let's suppose that we are in the state called Q1, Q2 of the DFA that I'm going to make. So all this means is that I could be in Q1. There is a way to get to Q1 of the NFA, and there's also another way to get to Q2. So how do I find out where I go on the input A, for example? Well, if there's a way to get to Q1, I think I should figure out where Q1 would have went on input A, right? Because there was a way to get to there. So where do I go from Q1 on input A?
Q0.
Q0. So I'm going to start keeping track of a set of states. So I have Q0 so far. And I don't think I can get anywhere else from Q1 on input A. What about Q2?
To Q1.
I think the only way to go is Q1. So the set of states is going to be Q0, Q1. And that's my state. Okay? So let's digest what I just did. I'm going to look at every single one of these states in this set, and I figure out first, where do I go on that particular input character, and then I combine all the results together, right? That's what I did here. The first one was Q0, second one was Q1, and then I combined all those results together. So let's see how to do this in general instead of just one example. So I have a set of states here called X. So I'm going to look at every single state in X and then figure out where it would have went in the NFA on input A in this case. So how am I going to combine the results together then? How do I put, well, first of all, what is the NFA's transition function output?
A set of states.
A set of states. How do I combine a bunch of sets together?
Union.
Union, right? So I'm going to do a giant union over every single one of those little states where they would have went. So I'm going to call little q in X. So this little q is taking the role of looking at Q1 first and then looking at Q2. And so how do I find what little q did on input A? How do I find that out? Oh yeah, the transition function of the NFA, because this little q is a state in the NFA, right? So to figure out where it went, I just look at its transition function, q on it. So I'm going to look up in the transition function all of those results, combine them together with one giant union. Okay? Is this? Yeah.
Sorry, the delta QA, so of the NFA, Q is a single.
State of the NFA, yes.
Okay, because we're only in one state at a time in an NFA.
Of the union, yes. Well, there's two different notions here. A computation in an NFA, you're only in ever one state. But in the DFA, there are many choices. I could have been in. It will only make one choice if I feed it to an NFA, but I am simulating all possible choices because the DFA doesn't have.
That's because in the DFA, each state is a set of substates
of the
NFA.
Yeah. Any other questions? Is this all there is?
The final states?
Oh, other than final states. I meant of the transition function. Is there something I forgot? Epsilon closure, right? Because think about, like, say, this example. Can I have a possibility of having an epsilon transition somewhere else? Yeah, I could have that, right? Because after I read a character, I could be here without having read anything else, right? So I think I should do epsilon closure after I do this whole operation. So I'm doing epsilon closure of this whole thing. Okay? So as we'll see, the common thing that students commonly mistake is they do epsilon closure first, then they do the union, or it's the other way around. You do the union first, then you do epsilon closure. But we'll see that when we get over there. All right? And of course, the thing that's left out is set of final states. So I better do final states. And the final states are always a set, so I better write down a set. Well, let's look at an example right here. Suppose I have a transition like this. How do I determine whether each of these states is a final state or not?
If an element in that substate is a member of the set of final states of the DFA.
Ah, yeah.
And the NFA.
Right. So remember, what does this mean? This means that there is a way to get to Q1, and there is a way to get to Q2. So what is the role of non-determinism? It says if there's a way to accept, it will take that choice. So if it got to Q1, there is a way to accept, right? And so therefore, I should make this a final state. Should I make this one a final state?
Yes.
Yeah, for the same reason. Good. And let's just note that F in this case is Q1, because that'll be helpful in a second. Okay? Oh, you have a question? Okay, so let's think about how we actually figured out whether this was a final state or not. So what did I do with these two sets? And figured out, okay, is there anything in common between them? How did I find that out? I did intersection, right? So if there was something in common, their intersection will have something in it. Suppose that this state instead was called Q0, Q2. Would this be a final state?
No.
No, because there's no final state written here. But if I look at these two sets, what's their intersection?
It's the empty set.
Empty set. So if it's not empty, then I should make it a final state. If it is empty, it's not final. Okay? So what should I do here? I should look at all subsets X of the set of states of the NFA here. So what is X in the DFA? X is a set of states in the NFA. What is it in the DFA? take a single state because a state represents a set in the NFA. So this is all that I really want right here. But what do I want to be true about X? Well, it better contain a final state of the NFA before. So how do I determine if X and F have anything in common? Intersection, right? A lot of confused spaces. Is there anything not clear about this? Or you just don't want to say it? Yeah.
So when X is a subset of Q, that's the Q of the NFAs.
Of the NFA.
So why wouldn't it be a subset of a power set of Q?
And X is an element of the power set.
Okay.
Because it's just some subset.
Right.
This is the set of all subsets. All this really means is that it's a state of the DFA, so we can put it in the final state for the DFA here. But I'm going to exploit the fact that it's a set of states in the NFAs because then I can do intersection. Whereas if it was just a state name, I couldn't do intersection before.
Okay.
Yeah, it's a little wonky. But what I want is that X has something in common with F, and we've just noted that the intersection better not be empty for that to happen. So X intersect F is not empty. So in this case, in the first one where I changed it to a 0, there was an empty intersection, so therefore I should not make it a final state. Okay? Does that make some sense, at least? Okay. So that'll be helpful when we do these in a second. But let's do these two examples first. So the first one says, I want all the strings in 0, 1 star such that it's the concatenation of two strings, x and y. X contains 0, 0 as a substring, and y starts with 1, 0, 1. All right? And I claim that it's regular. So when you see this, what should I be producing at the end? DFA. Would you let me use an NFA? Yeah, you should, because I'm in the process of converting to a DFA, so we're fine there. All right, well, is there anything that in this description that jumps out to you as being kind of important? That is true, in which case we could do product construction, but is there something even more important here? Concatenation, right? So I have concatenation. So, do we have closure under concatenation?
Yes.
Yeah. So if I can make an NFA or DFA for this, and an NFA or DFA for this part, I'm golden. So let's make a DFA or NFA for both. Will you let me do an NFA for both parts? Yeah, there's no reason not to. So, other than simplicity. So, let's do X contains 0, 0. Yeah.
But we don't know whether NFA is closed under concatenation. We know about DFA, but we haven't proved for NFA.
No, we did. We'll see how to do it. Well, I haven't proved it here, but we've proved it in class. We'll see how to do it again here. Any other questions? Okay. So how do I do contain 0, 0? So it seems a little, and it's actually one of the quiz questions, somewhat related to this. If I have a arbitrary string that contains 0, 0 in it somewhere, do I care what happens before 0, 0? No, I don't care, because as long as it contains the 0, 0, I don't care. What about afterward? Again, I don't care. So this actually really helps us here for non-determinism. Maybe what I can do is I can just arbitrarily read characters off the input, and then the machine's going to say, okay, I'm going to guess right now, I'm going to start reading the 0, 0. Because it can't see into the future, but it's going to guess that it's going to see the 0, 0 here, right? So maybe what we can do then is have a start state that just loops on itself, reading off the characters off the input. So 0, 1 as a self loop. And then now I'm just going to guess I'm going to see the 0, 0 right now. So I'm going to see a 0, Q1 to Q2. Okay. So what do you think Q2 should be then?
Final state.
It should be a final state. Good. Is this all there is to this NFA? What have I forgotten?
The one. Well, you don't have to make it a total function, do you?
Formally it is, but you define all the other ones to be empty set. But is there any other non-empty transitions I should put?
Should have Q2 loop on itself.
Yes, I should have Q2 loop on itself. As is, what is the language of this NFA? It ends with 0, 0, right? Because if I read anything, I'm toast, right? So I want to have to be able to read things afterwards. So I better loop on myself. Okay. Cool. Now I want to do y starts with 1, 0, 1. Does that seem somewhat similar? Yeah, so how do you think I can approach doing that one?
Well,
What does the first transition have to be?
a 1.
1. Second one is?
0.
0 and 1. So I better not have the situation where I do a looping at the beginning, right? Because then it can just stay there. I want to transition out immediately. So let's do 1, 0, 1, Q6. What should Q6 do, or is it a final state? It should loop on everything, because after I read 1, 0, 1, I don't care what happens. And I think it should be final, right? Because once I see 1, 0, 1 at the beginning, I'm already set. Okay? You see how we did that? Am I done with the whole problem? No. Of course I ask it in that weird way, right? How do I actually do the rest of the problem then? I gotta concatenate the two machines together. And how am I gonna do that?
Make the final state of the one as a start state.
Okay, so I gotta glue these two machines together somehow. And remember, concatenation is some string of the first machine, followed by immediately a string from the second machine. Well, that means that if the first machine accepts the string, then I better transition right over to the second machine. So what transition should I do? Epsilon. So I should do an epsilon transition from here to there. And I shouldn't make this not final. Sorry. Is this it?
Wait, hold on. But we're starting with 1. Oh wait, sorry. Y is after the double zeros.
Yeah.
Okay.
Is this it?
You have to show the final state.
Ah. Should this be a final state or no? No, and why is that? Because it's concatenated, but in this case, what would happen? I claim, if I left this final, I don't need this part of the machine. 3, 4, 5, or 6. And why is that? Because if I read through the 0, 0s, I can just stay in Q2 until I read the whole string. As long as there is a way to accept, it will make that choice. Okay? So, by making this final, then I'm changing the language of what I want. So I should make this not final. Then now, if it wants to accept, it will have to go through the entire machine. And that's what I want. Okay? Does that make sense? How are we able to do that? Any questions? Okay. So I want an NFA for L star now. Yeah.
So let's say we are not able to create the NFA. Can we create a DFA and concatenate them?
I could have made a DFA for both parts and then did the epsilon transitions in between. Yeah, that's totally fine too. These didn't have to be NFAs, but it's much easier for these two problems to make NFAs. But you can certainly have made a DFA first. All right, and actually for this second part, it doesn't matter if it's DFA or NFA either. All right, so how do we show closure under star then?
Put a final state at the beginning and then after the last state being towards it?
Yeah, so something about if we had a black box, well, red now, right? Terrible jokes by Ryan. All right, so let's say that this had two final states, let's say. And then the suggestion was, well, since we want star, we gotta be able to come through the machine as many times as we like. And once we go through a machine, the only way out is through the final states of the machine itself. So what I think would be a good suggestion, and was the suggestion, is to make a new start state. Change markers. That's better. And what should I do with this new start state?
It should be a final state.
It should be a final state, and why is that?
Because if we have the case that we have 0 repetitions of L,
Yeah, and so what string would that be?
epsilon.
Epsilon, yeah. And so that's a key point. Epsilon's always in the star of any language. And so how do I hook up this new the start state? Epsilon transitions to where? Oh, the old start state, good. And what about these two states? I actually could, actually no I can't in general, and you can actually show that you can't. I need to leave these final. Because it could be that I have a, actually no, I could make them non-final. Because I could epsilon transition over to here. But I want to touch the machine as little as I can. Modify it as little as I can, but you're right, I can. So what should I do with these two final states?
Epsilon transition back to the new start state.
To the new start state. Right? I need to transition back so that I can make my way through the machine as many times as I like. And you can actually prove that if you can't come back purely to the old start state, you should go back to the new start state.
And so this red box NFA represents the NFA we just built here,
Yeah.
number 1.
Yeah, so, we're going to work on that in a second.
Okay.
Good question?
Yeah, the old final states, are they gonna stay final or?
Yeah, I want to touch the machine as little as I can, so I'm going to keep them final in this case. But I could make them non-final, but I don't want to be clever. Yeah.
For that state, do we need to make?
Which one? This one? This one's the final state.
Is it necessary to make final?
Yes. What string is always in the star of any language? Epsilon. So if this state happened to not be final, I better make this one final. Because then I wouldn't accept the empty string, which I need to accept.
So the star contains the star.
Yeah, but I could have just said that this is a DFA, at which point it doesn't have an epsilon transition. So I don't know what's in here, so I can't make any assumptions. It needs to work in general. Okay? Does that make sense? Any other questions? Okay, so how do I fix this NFA already built? So what do I need to do? Add a new start state. Good. So I add a new start state. I'm going to call it QS. Better be final because this state's not even final anyway. And I think I need to make an epsilon transition to the old start state. And what else? What else do I do?
Epsilon Q6.
Yeah, epsilon from Q6 back to QS. And that's it. Very, very simple transformation. Any questions on this? Okay. So let's actually start transforming an NFA to a DFA. Okay. So now, when you look at this NFA, is there something that makes it a lot easier to convert to a DFA? Is there something absent?
Epsilon.
Epsilon transitions, right? So I don't even need to worry about epsilon closure this time because there aren't any transitions. So what should be the start state of this DFA that I'm going to make?
Q0.
The Q0, yeah. So it's not going to have any other state because there's no epsilon transition. Good. So now I got to figure out where it goes on input A and B. So where does Q0 go on input A? Q2. and nowhere else, so we gotta check that, because I'm gonna have more transitions. Q2 and nowhere else. And so the names here, it doesn't have to have the curly braces in here, it's just for convenience for me. All right, what about Q0 on B? Where does it go? It goes to Q1 and nowhere else, so I'm gonna write Q1 here. All right, let's do Q2. What about Q2 on A? I go to Q1, that's the only place I can go. And I have that state already, so I'm gonna put that there. Here's the interesting part. What about Q2 on B? Where do I go? Q1 and Q2 here. I don't have a state called Q1, Q2, so I'm gonna make one. Q1, Q2, make it a state. You see, like I have multiple computations, and I'm just squashing them down to one state. Q1 on input A, where do I go? Back to Q0, and I already have that state, thankfully. So I'm gonna make a transition back. Q1 on B, where do I go? Nowhere. So what does that represent? Some dead state, and what set is it? Empty set, right. So I'm gonna make a new state called empty set. And that was on B. What do you think the empty set does on anything?
Loops to itself.
Loops to itself. If I'm currently nowhere and I read something, I think I'm still currently nowhere, right? Okay, so that takes care of that. So let's do the Q1, Q2 state. Q1, Q2 on input A, where do I go?
Q0, Q1.
Q0, then, so I'm gonna start writing down a set. That's what Q1 did to Q0. Q2 took me to Q1. And I don't have this state yet, so I'm gonna make it on input A. What about on B for Q1, Q2? Well, from before we know that Q1 doesn't go anywhere on B, so that's currently empty set. Q2 on A, B. Where's Q2 taking on B?
To itself.
Q1, Q2. So what's the final result?
Q2.
Empty set with Q1, Q2.
Q1, Q2.
Q1, Q2, right? Because empty set union anything, I think it's the anything, right? Oh, I have that state already. So I'm gonna solve it. Okay. Q0, Q1. Where do I go on input A?
Q2.
I go to Q2 from Q0, and Q1 takes me where?
Q0.
To Q0. So I have Q0, Q2, and I don't have that state yet. Q0, Q2, and I go there on A. What about B from 0, 1? So I just usually say the subscript instead of Q every time. Where do I go from 0, 1 on B? Well, 1 takes me nowhere. Q0 takes me to Q1. So I just go back to Q1 on B.
Like on Q1, Q2 on B, doesn't it just go to Q2 instead of to itself?
Q2 goes to Q2.
Q2 goes B here.
Right, and then,
B.
but Q1 doesn't go anywhere.
Yeah, so empty set union Q1, Q2.
So how does Q1 go to itself on B?
I'm in Q2. I'm just looking at every possible state in here and then combine all the results together.
Right, so Q1 goes nowhere on B.
Nowhere, it's empty set.
Empty set, and then Q2 goes to Q1.
And?
Itself.
Oh, there's two transitions.
Yeah, yeah. So
Okay.
sometimes you forget about the transitions here. It's important to take care of all transitions. 0 and 2 on A, where do I go? 0 takes me to 2. 2 takes me 1. So 1 and 2, I have that already. 0 and 2 on B, where do I go? 0 takes me 1, 2 takes me 1 and 2. I've seen 1 twice, so it doesn't matter. So the final result is 1 and 2. Oh, I have that state and transition already. Lucky me. Am I done? Ooh, yeah, final states, right? Please be right about this. What is the language of the DFA as it is right now?
Nothing.
Nothing, which is?
Empty set.
Empty set. Good. So how do I find what's the final state here? Which state has Q1? Has the non-empty intersection, right? So Q0 doesn't have it. Q2 doesn't have it. Ooh, Q1 is right here. Q1's here again. Q1's here. Ooh, not here, not here. Okay? You see how we were able to do that? We're just looking at everywhere you can go and then just put all the results together. Okay? Any questions about that? So now we have a larger example, and dun 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 dun, we have epsilon transitions. So now we actually need to worry about epsilon closure. So what should my start state be of this DFA that I'm going to make? Well, it's definitely always going to contain the start state of the NFA, which is Q0. Is it going to have anything else? No, and why is that? No epsilon transitions out of Q0. So Q0 is going to be my state. Now we got to figure out where it goes on A and B. So let's do B first. Where does Q0 take me on B?
Itself.
And itself. Yeah, I don't have a state called 0, 1, so I'm going to make that a new state, Q0, Q1. Be careful in this one. Q0 on A, where do I go? Q2? Is it Q3? Do I go to Q3 on input A from Q0?
Yes.
On input A, is there a transition from Q0 to Q3 on input A? No. So where do I go from Q0 on input A? Q2. So I'm going to write this down. Do I go anywhere else from Q0 on input A? No. Now, what's the epsilon closure of Q2?
Still Q.
Itself and Q3. See, that's what I was saying before. Students commonly mistake doing the epsilon closure prematurely. So you do the union first, then you do epsilon closure. So I did the union first, then I add the epsilon closure later. So this is my new state. Okay. Let's do Q0, Q1. Q0, Q1 on input B, where do I go? Q1 and itself, Q0. So what's the epsilon closure of Q0, Q1? Itself, right? Because there's no epsilon transitions coming out of it. So I can just self-loop on B, like that. Okay. Q0, Q1 on input A, where do I go?
Q0, Q2.
Q0, Q2, all right. Anywhere else? I don't think so. Where else? Oh, okay. What is the epsilon closure of Q0, Q2?
Q3.
0, 2, and 3. I include the one I'm currently looking at. So I add on Q3. So this goes here on A. Okay. Let's do 2 and 3. So where do I go on input B from 2 and 3? So where does 2 take me? 1 and 4. So I'm going to come over here and write down Q1, Q4. Where does 3 take me on B? Just itself. So I usually write these in ascending order. What is the epsilon closure of 1, 3, and 4? Itself, right? None of these states have epsilon transitions coming out of them, right? So therefore, I'm going to make this a state. And that was on a B. Okay. 2 and 3 on input A. Where do I go? Well, let's write down the states I can get to. I can get to 1, and I can get to 2. So Q1, Q2. Where does Q3 take me on input A?
Q4.
Q4 only. All right. What's the epsilon closure of 1, 2, and 4? 1, 2, 3, 4. See, it's just simple as counting, right? So I come here on A. All right, let's do a few more. 1, 3, and 4, where do I go on input A? So where does 1 take me on A?
0.
0, good. 2, 0. Q3 on A, where do I go?
1 and 2.
Q3 on A?
Q4.
All right. Q4 on A? Empty set, so I don't write that down. Epsilon closure of 0 and 4. 0 and 4 itself. Good. We can actually note that anything that has a 2 in it will have 3 added in. If it doesn't have a 2, then it'll be just itself. All right, so that was on a yeah. 1, 3, and 4 on input B. Where do I go? Q1 on B, where's it go?
Nowhere.
Nowhere. We're good. Q3 on B, where do I go?
Q3.
Itself, so I write down Q3. Q4 on B?
Nowhere.
Nowhere. Epsilon closure of Q3?
Q3.
Itself. So now I make that a. I think this one's going to finish sometime soon, hopefully. Hopefully. So what does Q3 do on input A? Q4, right? It goes to Q4. So A goes to, I think we know now that epsilon closure of Q4 is itself. What does Q4 do on anything? Empty set. Good. So A and B goes to empty set, which will do. So this one's actually getting quite big. 1, 2, 3, 4 on input A. Where do I go? 1 takes me to Q0. Q2 takes me on A to where? 1 and 2. So Q1, Q2. 3 on A, where do I go? 4. Q4, we already know doesn't take me anywhere. What is the epsilon closure of 0, 1, 2, 4? 0, 1, 2, 3, 4. So I don't think we'll finish this in the time. So let's just say that we actually finished this. I invite you to actually finish it, but let's just say we did. Am I done if this is the finished DFA?
No.
No, I don't have final states, right. So how do I determine what's final state and what's not? Anything that has a 0 or 4. So this has a 0, this has a 0, this has a 0, nothing, 4, both, no, has 4, this has everything. This has. Okay. Any questions about any of this? Yeah.
Would we expect to do this kind of conversion on an exam?
Yes.
Of this length?
Probably more like this.
Okay.
But maybe slightly larger. Look at past tests, you'll see. Yeah.
If agree DFAs in NFA, but reversal bundle, right?
Yes, because I can have epsilon transitions.
So, is NFA closed under union and intersection?
Actually, one of the quiz questions was about closure under intersection for NFAs, whether that's true or not. There always is an NFA for the intersection, but there may or may not be a nice way to actually algorithmically make it. But there always is one because they recognize the regular languages.
So it's closed. I mean, it's closed.
Yes, it is closed, but there's not necessarily an algorithm to do so.
For
Okay?
union also.
For union, there is. And it's actually pretty easy. So if you have the two NFAs right there, or DFAs, it doesn't matter. New start state, epsilon transition to the old ones, like that. Now go to the union. Any other questions?
Is there an attendance sheet?
There's a sign-in sheet. All right, I'll see you next week.